My friend, welcome. If this is your first time here, this video is made to help you fall asleep while learning something extraordinary. Tonight, we'll drift through the quantum universe, calmly, slowly, one idea at a time. Let your day fade, and let the science carry you into rest. Chapter 1. Quantum Basics. Quantum physics begins with an idea that seems simple, but immediately reshapes everything we believe about the physical world. Energy does not flow continuously, but instead arrives in tiny, indivisible packets called quanta. When Max Planck introduced this concept to explain the spectrum of glowing heated objects, he discovered that nature itself behaves in discrete steps rather than in smooth lines. That single insight laid the foundation for an entirely new description of reality. If energy comes in quanta, then the interaction between matter and radiation must obey rules far more granular and precise than classical physics ever required. This is the quiet entry point into the quantum world, where familiar expectations begin to dissolve and deeper patterns emerge. One of the most striking consequences of quantization is the behavior of electrons. An electron is not simply a small sphere orbiting a nucleus, even though early atomic models imagined it that way. Instead, an electron has a dual nature. Under some conditions, it behaves like a localized particle, while under others, it behaves as a spread-out wave. This wave character is not an analogy, but a measurable fact. When electrons pass through a barrier with two openings, they produce an interference pattern characteristic of waves, even when they go through one at a time. Yet when a detector is placed to observe which opening each electron passes through, the interference pattern disappears, and the electrons behave like individual particles landing in particular places. The electron does not commit to being one thing or the other. Instead, it carries both behaviors within its quantum description, revealing one or the other depending on how it is examined. The quantum framework also tells us something profound about the idea of stillness. In classical physics, an object can be perfectly at rest if no forces act upon it. In quantum physics, however, absolute rest is impossible. Every physical system possesses what is known as zero-point energy, the lowest possible energy allowed by quantum rules. Even in this lowest state, the system retains a faint vibration, a kind of eternal trembling that arises from the uncertainty built into quantum mechanics. This is not heat, motion, or noise in the usual sense. It is the unavoidable baseline of existence itself. Molecules, atoms, and even the fields that fill the universe retain this gentle energy, which influences phenomena ranging from the stability of atoms to the delicate interactions inside superconducting circuits. Modern physics views the world not as a collection of isolated particles, but as a network of quantum fields extending through all of space. Each type of particle arises from a particular field: the electron field, the photon field, the quark fields, and so on. A particle is simply a localized ripple or excitation of its corresponding field. The fields remain in place, whether or not excitations are present, and even the empty vacuum of space is not truly empty. Instead, it is alive with restless fluctuations, as the fields momentarily create and annihilate tiny excitations. These fluctuations are central to many effects, including the stability of atomic structures and the extremely precise behavior of certain energy levels. The picture that emerges is not of a void, but of an active quantum backdrop that permeates every region of the universe. A natural consequence of this framework is that particles cannot be assigned exact positions in the way classical physics would prefer. Before measurement, a particle is described by a wave function, a mathematical object that encodes probabilities rather than definite outcomes. The wave function spreads over space like a soft cloud, assigning different likelihoods to different regions. It is not that the particle has a precise but unknown position within this cloud. Rather, the position is genuinely undefined until the moment of measurement. Only when a measurement occurs does the wave function narrow into a localized event, revealing one specific position. This distinction between unknown and undefined is one of the most subtle and revolutionary aspects of quantum theory, and countless experiments have confirmed the probabilistic interpretation. This uncertainty extends to the structure of atoms themselves. Atoms are mostly empty space, not because matter is hollow, but because the wave function of an electron occupies a wide region around the nucleus. The electron does not orbit the nucleus like a planet around a star. Instead, it forms a standing pattern of probability, a stable distribution governed by quantized energy levels. These allowed energy levels prevent the electron from collapsing into the nucleus, and the shape of the wave function determines the size and behavior of the atom. Because electrons occupy only certain energy states, atoms remain stable and structured. These discrete energy levels give each element its characteristic spectral lines, providing a quantum fingerprint that astronomers use to identify matter across the cosmos. Light itself reveals another essential quantum property. While classical physics treats light purely as a wave, experiments show that it also behaves as a stream of individual particles called photons. Each photon carries a specific amount of energy determined by its frequency. When light interacts with matter, it does so one photon at a time, transferring energy in quantized packets rather than in continuous flows. This explains phenomena such as the photoelectric effect, where electrons are ejected from a surface only when the incoming light has a high enough frequency to deliver photons of sufficient energy. The quantization of light is not merely a feature of extreme conditions. It is present in everyday technologies such as cameras, solar cells, and even the way human eyes detect brightness. Superposition is one of the conceptual pillars of quantum physics. A quantum system can exist in multiple states simultaneously, combining alternatives into a single, unified description. An electron can be in several energy levels at once, a photon can follow multiple paths, and atoms can occupy distinct positions simultaneously. These superposed states evolve in time until a measurement is made. At that moment, the possibilities narrow to a single outcome. Superposition does not imply that we simply lack knowledge of the true state. Rather, the system genuinely embodies a range of possibilities before observation. This principle allows technologies like quantum computing to perform operations on many states in parallel, harnessing the richness of quantum mechanics for powerful new forms of computation. Measurement plays a central role in determining the behavior of quantum systems. When a measurement occurs, the wave function transitions from a spread-out distribution of possibilities to one specific result. This process is often described as wave function collapse, although the underlying mechanics remain a topic of ongoing investigation. What is clear from experiments is that the act of measurement is not passive. It changes the system. Measuring the position of a particle alters its momentum, Observing which path a particle takes destroys interference patterns. Interacting with a quantum system transfers information and modifies the state. This sensitivity to measurement is not a flaw, but a defining feature of quantum behavior. At the heart of quantum mechanics is probability. Unlike classical probability, which reflects uncertainty due to incomplete information, quantum probability is fundamental. It describes genuine indeterminacy. The wave function evolves predictably according to the rules of quantum theory, but the outcomes of individual measurements cannot be foreseen with certainty. Instead, quantum mechanics provides probabilities for each possible result. When large numbers of events are measured, the statistical patterns match the probabilistic predictions of quantum theory with extraordinary accuracy. This probabilistic nature does not imply randomness without structure. Rather, it reveals a universe where uncertainty is woven into the fabric of reality in a consistent and mathematically precise way. Together, these principles describe a world that is both richer and more subtle than everyday experience suggests. Energy arrives in discrete steps. Electrons behave as both particles and waves. Nothing rests completely. Even the vacuum vibrates with zero-point energy. Space is filled with quantum fields that fluctuate continuously, shaping the behavior of particles and forces. Atoms maintain their structure because electrons occupy quantized states within a landscape of mostly empty space. Light itself consists of quantized photons. Superposition allows systems to exist in many configurations at once, while measurement selects only one. And probability governs the outcomes of quantum processes, not as a sign of ignorance, but as a fundamental feature of nature. As you reflect on these ideas, it becomes clear that the world you experience each day rests upon layers of behavior far stranger and more intricate than anything visible on the surface. The chair beneath you, the air around you, the light entering your eyes, and even the atoms within your body follow rules shaped by quantized energy, fluctuating fields, and probabilities that unfold quietly beneath awareness. There's something calming in recognizing how much complexity the universe handles without your attention. You do not need to track the trembling zero-point energy inside every atom or the probabilities shaping every electron. The universe manages these details faithfully, moment after moment, allowing you simply to exist within it. For tonight, you can let the vast machinery of quantum physics continue its work while you rest, carried effortlessly through a world far deeper than it appears. Chapter 2: Quantum Particles. In the quantum description of nature, what we call a particle is both familiar and profoundly strange. It behaves like a point-like object when observed, yet its deeper identity is tied to fields spread across all of space. Within this framework, every type of particle has precise, fixed properties and follows rules that hold across the entire universe. One of the clearest examples is the electron. All electrons are perfectly identical, not merely similar or manufactured to the same standards, but absolutely indistinguishable in every measurable way. Their mass, charge, spin, and magnetic moment are the same no matter where they appear or how they are produced. This perfect identity is not an assumption. It is confirmed through countless experiments in atomic physics, spectroscopy, and particle physics. If electrons differed even slightly, atoms would not have consistent structures, chemical reactions would not behave reliably, and the periodic table would fall apart. Instead, The universe treats every electron as an instance of the same underlying excitation of the electron field, guaranteeing their sameness everywhere. The idea that particles are excitations of fields is essential for understanding the quantum world. Rather than imagining particles as tiny marbles, quantum field theory describes them as small ripples or vibrations within a continuous field. When a particle is created, the field is briefly excited. When a particle is annihilated, the excitation disappears. These excitations can move, interact, and carry energy, but they are never detached from the fields that produce them. This interpretation explains why particles pop in and out of existence during high-energy collisions or decay processes, and why their properties remain so consistent. What appears to us as a particle is simply the smallest possible unit of a field's activity. Even the vacuum of space, which might seem like a calm, empty backdrop, reveals surprising complexity. Quantum fields do not sit still, even when they are in their lowest energy states. Instead, they undergo constant fluctuations, giving rise to what physicists call virtual particles. These ephemeral excitations appear briefly and then vanish, borrowing energy in a way permitted by the uncertainty principle. Virtual particles are not directly observable as stable entities, but they influence measurable phenomena such as the energy levels of atoms, the strength of forces, and the behavior of particles in high-energy experiments. Their existence highlights that emptiness in the quantum sense is never truly empty. Space is a dynamic, restless medium where fields fluctuate continuously, shaping the behavior of the particles that emerge from them. Among the particles emerging from these fields, quarks stand out for their unusual confinement. Quarks form the fundamental building blocks of protons and neutrons, but unlike electrons, they cannot be isolated. Every experiment attempting to separate quarks only produces more particles made of quark combinations. This phenomenon, known as confinement, arises from the nature of the strong interaction. The force between quarks does not weaken with distance. Instead, it grows stronger as quarks are pulled apart. When enough energy is applied to separate quarks, that energy materializes as new quark-antiquark pairs rather than releasing a single quark into isolation. As a result, quarks always remain grouped in twos or threes, forming composite particles such as mesons and baryons. This distinctive behavior marks them as fundamentally different from electrons, photons, or neutrinos. Photons, the excitations of the electromagnetic field, offer a contrasting perspective. A photon has no rest mass, which means it cannot exist at rest and always travels at the speed of light. This property is baked into the structure of electromagnetism and has been confirmed in precision tests over many decades. Without mass, photons do not require energy to accelerate. They always move at the same universal speed through a vacuum. Photons carry momentum and energy, influence charged particles, and enable the electromagnetic interactions that shape chemistry, biology, and the behavior of light across the universe. That they lack rest mass does not diminish their role. Instead, it allows light to propagate across cosmic distances without slowing down, carrying information from stars, galaxies, and distant events to observers on Earth. In contrast to photons, neutrinos possess a tiny but non-zero mass and interact extraordinarily weakly with matter. Trillions of neutrinos from the sun pass through your body each second without leaving any noticeable trace. They barely interact because they participate only in the weak nuclear force, which operates over very small distances and has limited influence compared to electromagnetism or the strong force. Neutrinos can travel through planets without scattering, penetrate dense astrophysical environments, and escape from regions where other particles remain trapped. Their ghostly nature makes them difficult to detect, yet they play essential roles in stellar processes, supernova explosions, and the evolution of the universe. Their existence also helped confirm that fundamental symmetries in particle physics behave differently than early theories predicted. Another remarkable quantum phenomenon tied to particle behavior is tunneling. Classical physics imposes strict boundaries. An object with insufficient energy cannot cross a barrier. Quantum mechanics, however, allows particles to tunnel through barriers even when they do not have enough energy to surmount them in the usual way. This effect arises from the wave-like nature of particles and the fact that wave functions extend into regions that classical objects cannot access. Tunneling is not rare. It appears in many settings, from radioactive decay to enzyme reactions in biology and the operation of modern electronic devices. It is one of the clearest examples of how quantum rules allow possibilities that defy classical intuition while still matching experimental evidence precisely. The classification of particles into fermions and bosons provides another essential layer of understanding. Fermions, such as electrons, protons, neutrons, and quarks, make up the matter that forms atoms and structures in the universe. They follow the Pauli exclusion principle, which prevents identical fermions from occupying the same quantum state. This principle explains the structure of atoms, the arrangement of electrons in shells, the stability of ordinary matter, and the behavior of dense astrophysical objects such as white dwarfs. Bosons, on the other hand, carry forces and mediate interactions between fermions. Photons mediate electromagnetism, gluons mediate the strong force, and other bosons mediate the weak interaction. Unlike fermions, bosons can occupy the same state, enabling phenomena such as lasers and superfluidity. This division between matter-forming fermions and force-carrying bosons is one of the structural pillars of particle physics. The symmetry between matter and antimatter emerges vividly in the relationship between electrons and positrons. A positron is the electron's antimatter twin, possessing the same mass but the opposite electric charge. When an electron and a positron meet, they annihilate, converting their mass into energy typically carried away by photons. Positrons are produced naturally in cosmic rays, radioactive processes, and in medical imaging technologies. Their existence confirms that the quantum world is built upon deep symmetries, even though the observable universe contains far more matter than antimatter. Understanding why this imbalance exists remains one of the open questions in modern physics. Muons, meanwhile, behave like heavy versions of electrons. They have the same charge and spin as electrons, but roughly 200 times their mass. Their heavier mass allows them to probe different regions of atomic and subatomic structures. Because muons decay quickly into lighter particles, they do not appear in ordinary matter, but they are constantly created in the upper atmosphere by cosmic rays. Experiments using muons help explore fundamental symmetries of nature, study the internal structure of materials, and test whether the standard model of particle physics is complete. Muons demonstrate that the family of particle types extends beyond the familiar, and that heavier counterparts exist even when they do not remain stable in everyday environments. Taken together, These insights reveal a world of particles that is both orderly and profoundly intricate. Electrons remain identical across the universe. Quarks never appear alone. Photons glide through space without rest mass. Neutrinos slip through matter with barely a whisper, and muons pass briefly through existence before decaying. Virtual particles flicker in and out of being as quantum fields fluctuate. Tunneling allows particles to cross barriers they should not, and the distinction between fermions and bosons shapes both matter and the forces acting upon it. Each behavior follows from the deeper structure of quantum fields and symmetries rather than from any classical picture of tiny billiard balls. As you reflect on these ideas, it becomes clear that the world beneath everyday experience is far more dynamic and interwoven than it appears. Even the simplest particle holds layers of complexity shaped by fields, symmetries, and fluctuations that operate beyond the reach of intuition. You are built from particles that have existed since the early universe, each one identical to its siblings across galaxies. There is a strange comfort in recognizing that the building blocks of your body follow timeless rules, participating in patterns that stretch across cosmic distances and deep into the fabric of space. You do not need to grasp every detail to feel connected to this vast, intricate structure. For now, it is enough to know that the particles composing you are part of a quiet, enduring order, carrying their properties through time as you rest within the same unfolding universe. Chapter 3: Quantum Waves. In quantum physics, the idea of a particle as a tiny solid point gives way to a more subtle and powerful concept. Every particle is described by a wave function. The wave function is not a physical ripple like a vibration on a string or a disturbance on a pond. Instead, it is a mathematical object that captures everything that can be known about a quantum system. Its shape, phase, and evolution encode how a particle might behave, where it might be found, and how it might interact with other systems. The wave function provides probabilities, not certainties, yet it does so with astonishing precision. When experiments are repeated under identical conditions, the distribution of outcomes always matches the predictions of the wave function. This has been verified through countless studies across atomic, molecular, and solid-state physics. One of the defining characteristics of a wave function is that it spreads out until a measurement is made. Before observation, the wave function extends over a region of space, assigning probabilities to various positions. This extended character is essential to quantum mechanics. It means that a particle is not located at a single point before being measured. Instead, it exists as a distribution of possibilities. The spread of this distribution depends on the system and the conditions it experiences. In free space, a wave function naturally broadens with time, reflecting the inherent uncertainty in a particle's motion. Only when a measurement occurs does the wave function narrow rapidly, localizing the particle. This process is often described as wave function collapse, and although its deeper interpretation remains debated, its observable consequences are consistent and repeatable. Interference is one of the most striking demonstrations of the wave-like nature of quantum particles. When a wave function encounters multiple paths, such as the two slits in a classic double-slit experiment, the different parts of the wave function can interact. They can merge, overlap, and produce an interference pattern that reflects both constructive and destructive combinations of probability amplitudes. Constructive interference enhances the likelihood of finding a particle in certain regions, while destructive interference reduces that likelihood. The resulting pattern reveals a hidden structure within the wave function, showing how quantum systems explore multiple possibilities simultaneously. This behavior is not limited to light or electrons. It emerges in any system whose coherence is preserved well enough to maintain wave-like behavior. Probability amplitudes lie at the heart of this interference. Unlike classical probabilities, which simply add together, quantum amplitudes can cancel or enhance one another depending on their relative phases. When two amplitudes align, they amplify the resulting probability. When they oppose, they reduce it. This interplay of amplitudes is what gives quantum mechanics its unique texture. It allows for phenomena such as tunneling, superposition, and entanglement, all of which depend on how amplitudes combine. Experiments have demonstrated interference patterns not only for electrons and photons, but also for atoms, complex molecules, and even entities composed of hundreds of atoms when cooled and isolated sufficiently. These results confirm that the wave function is a universal description that applies to all matter. Inside atoms, wave functions take on the form of standing waves. Electrons in atoms cannot occupy arbitrary energy values. Instead, they form stable patterns that fit around the nucleus in ways allowed by the rules of quantum mechanics. These patterns are the atomic orbitals familiar from chemistry, though in their true form they are probability distributions rather than fixed paths. The standing wave nature of these orbitals determines the allowed energy levels of the atom. When an electron transitions between these levels, it absorbs or emits light in quantized amounts, matching the difference between the energy states. This gives rise to the spectral lines characteristic of each element. The stability of these standing waves helps explain why atoms have consistent sizes and structures, which in turn gives rise to the stable behavior of matter. Wave function collapse represents a fundamental shift in the behavior of a quantum system. Before measurement, a particle is described by a spread-out wave function containing many possible outcomes. After measurement, only one of those outcomes is realized, and the wave function contracts sharply around that result. Physicists continue to explore the meaning of this transition, but they agree on its observable consequences. It is not that the particle moves from one location to another. Rather, the wave function updates to reflect the new information gained from the measurement. Subsequent predictions depend on this updated state. The collapse is therefore not a physical motion, but a change in the description of the system, marking the moment when possibilities give way to a single observed outcome. Quantum systems can also occupy multiple modes at once. A mode can be thought of as a particular pattern of motion or vibration associated with the wave function. For example, light in a cavity can exist in several frequency modes simultaneously, and electrons in solids can occupy different momentum states that overlap. The ability to inhabit multiple modes is central to phenomena such as superposition and coherence. It allows quantum bits to encode complex combinations of states and underlies behaviors observed in superconductors, lasers, and quantum sensors. Modes interact with one another through interference, shaping the evolution of the system in ways that classical intuition does not predict. Coherence is what allows these wave-like behaviors to persist. A quantum system is coherent when the relative phases of its wave function remain well-defined over time. Coherence makes interference possible preserves superpositions, and enables delicate quantum effects like entanglement. When coherence is lost, usually through interactions with the environment, the system's wave function no longer displays clear interference patterns. This loss of coherence explains why macroscopic objects do not exhibit quantum interference in everyday conditions. They interact with their surroundings too strongly to maintain the delicate phase relationships needed for wave-like behavior. Nevertheless, scientists can create conditions where coherence is preserved for unexpected periods, enabling experiments that probe the boundary between quantum and classical worlds. One of the earliest insights connecting waves and particles came from the proposal that all matter has a wavelength. This idea, known as the de Broglie hypothesis, states that the wavelength of a particle is inversely proportional to its momentum. While this wavelength is extremely small for everyday objects, it becomes significant for electrons, atoms, and even certain molecules. Countless experiments have confirmed that matter waves are real. Electrons diffract through crystals, atoms form interference patterns when passed through gratings, and even large molecules composed of dozens or hundreds of atoms exhibit wave-like behavior when cooled and slowed. These results show that quantum mechanics applies universally, not only to the smallest particles but to all physical systems. Large molecules showing interference was once considered impossible. Early physicists believed that only single atoms or tiny particles could maintain coherence long enough to interfere with themselves. However, as experimental techniques improved, scientists observed wave interference using molecules made of dozens, then hundreds of atoms. The key is maintaining coherence. The molecule must remain in a sufficiently isolated state so that its internal motions and interactions with the environment do not reveal which path it takes. When this isolation is achieved, even complex molecules behave like waves, forming interference patterns that match quantum predictions. This discovery underscores how deeply wave-like behavior permeates the quantum world, regardless of the size or complexity of the objects involved. The wave-based description of particles does not contradict their particle-like behavior. Instead, it provides a richer and more complete framework that encompasses both. When measured, particles appear localized, triggering the collapse of the wave function. But between measurements, their behavior reflects the full structure of the wave function, which spreads, interferes, and evolves smoothly according to quantum laws. This dual character is not a flaw or a contradiction. It is a fundamental property of the world at small scales. Accepting this duality requires a shift in intuition, but once embraced, it offers a profound understanding of the mechanisms underlying chemistry, electronics, optics, and the stability of matter. Reflecting on these ideas, it becomes clear that the wave nature of particles is not a peripheral curiosity, but the foundation of quantum mechanics. The world you experience, built from atoms and molecules, rests upon wave functions shaped by interference, coherence, and probability. These wave functions determine how atoms bind, how materials conduct electricity, how light interacts with matter, and how microscopic processes unfold. Even though these waves operate far below the scale of everyday perception, their influence extends everywhere. They shape the structure of the universe and the behavior of the particles within your own body. And there is a quiet, existential comfort in knowing this. The particles that compose you are guided by wave functions that have evolved uninterrupted since the earliest moments of the cosmos. They spread, interfere, and collapse in patterns that repeat across galaxies and within every atom of your being. You are, in a very literal sense, part of the same continuous fabric of quantum waves that fills the universe. As you end your day, you can let this understanding settle gently in your mind. The waves that govern the smallest particles continue their silent rhythm, whether or not you pay attention. You are carried within those rhythms, part of a structure far older and more expansive than any moment of thought or concern. Chapter 4: Superposition. Superposition is one of the central ideas of quantum mechanics, and also one of its most challenging. In the classical world, an object cannot be in two places at once, nor can it move along two paths simultaneously. Quantum systems break this intuition. A particle can be in many states simultaneously, described not by a single value, but by a combination of possible values weighted by probability amplitudes. This is not simply ignorance about which state the particle is in. Rather, the particle genuinely occupies multiple states until a measurement reduces those possibilities to one outcome. Superposition defines how electrons behave in atoms, how photons propagate through optical systems, and even how molecules move and vibrate. It lies at the heart of the quantum description of nature. One of the clearest demonstrations of superposition comes from the famous two-slit experiment. When an electron approaches a barrier with two openings, its wave function spreads toward each slit. If both slits are open and no measurement is performed to determine which slit the electron passes through, the electron behaves as though it travels through both. Its wave function moves through the two openings simultaneously, and the overlapping parts of the wave function interfere with one another. When electrons arrive at a detection screen, they form an interference pattern typical of waves, even when fired one at a time. This pattern would be impossible if electrons traveled through only one slit each time. It arises because each electron exists in a superposition of the two possible paths, and the paths interfere before collapse. Atoms exhibit similarly surprising behavior on larger scales. Under sufficiently controlled conditions, an entire atom can be placed in two locations at the same time. Experiments with cooled atoms in optical traps or interferometers show that atomic wave functions can split and later recombine, producing interference effects that reveal their underlying superposition. The atom does not divide into two separate pieces. Rather, its wave function evolves into a state that includes two spatially distinct components. This phenomenon highlights that superposition is not limited to subatomic particles, but extends to systems with many internal degrees of freedom, as long as coherence is preserved. Superpositions, however, are fragile. They decay through a process known as decoherence. When a quantum system interacts with its environment, whether photons, air molecules, thermal vibrations, or even internal fluctuations, the coherence that maintains superposition begins to degrade. The environment effectively records information about the system, producing entanglement between them. Once enough information has leaked into the surroundings, the interference patterns that rely on coherent superposition disappear. Decoherence explains why macroscopic objects do not display quantum interference in everyday life. It bridges the gap between the quantum and classical worlds, showing how familiar, definite outcomes emerge from underlying superpositions. Spin provides another example of superposition. The spin of a particle is a quantum property that does not have a direct classical analog. Before measurement, a spin can point in multiple directions simultaneously. If a spin is prepared so that it is aligned with a particular axis, it exists in a definite state relative to that axis. But relative to another axis, it can be in a superposition of spin-up and spin-down states. Only when it is measured along a chosen axis does it yield one specific outcome. This phenomenon allows for precise control of spins in techniques such as nuclear magnetic resonance and in the functioning of quantum bits used in computation. Quantum bits, or qubits, rely entirely on superposition to store and process information. Unlike classical bits, which hold a value of 0 or 1, a qubit can encode a combination of 0 and 1 simultaneously. This combined state persists until the qubit is measured. The richness of quantum computing arises from manipulating multiple qubits in superposed states, creating complex patterns of probability amplitudes. These patterns allow quantum computers to explore many possible solutions in parallel. Successful quantum algorithms depend on preserving coherence long enough for interference effects to amplify correct answers and suppress incorrect ones. Light also demonstrates superposition through its polarization states. A photon can be polarized horizontally, vertically, or at any angle between these orientations. But before measurement, it can also exist in a superposition of polarization states. This means a photon can be prepared so that its polarization is simultaneously horizontal and vertical with specific amplitudes. Interference experiments using polarized light exploit this property to measure small physical effects and to transmit information securely through quantum communication protocols. Polarization superpositions are robust, making photons ideal candidates for quantum information tasks. Superposition also appears in superconductors, where currents can exist in a superposed state. In certain conditions, a superconducting loop can support persistent currents flowing clockwise and counterclockwise simultaneously. These superposed currents form the basis for some types of qubits, known as flux qubits. The persistent current in a superconductor is a macroscopic quantum phenomenon involving the coordinated motion of many electrons acting as one. This highlights that superposition can extend to systems containing large numbers of particles, provided they share a coherent quantum state. Molecules, too, display superposition in ways that were once thought impossible. Internal vibrations, rotations, and electronic configurations can become superposed when molecules are cooled and isolated from their surroundings. In certain molecular interferometry experiments, molecules composed of dozens or even hundreds of atoms have been shown to produce interference patterns that reveal underlying superpositions of internal states. These results reinforce the idea that quantum superposition does not disappear with complexity. Instead, it becomes increasingly difficult to maintain because decoherence is harder to suppress in large systems. Underlying all these phenomena is the fact that superposition enables quantum interference. When two or more components of a wave function overlap, their phases determine how they combine. Constructive interference enhances amplitudes in some regions, while destructive interference reduces them in others. This delicate interplay creates the structured patterns seen in double-slit experiments, atomic interferometers, and molecular diffraction. Interference lies at the heart of quantum mechanics, and superposition provides the mathematical framework that makes interference possible. As we move through these examples, it becomes clear that superposition is not a decorative feature of quantum mechanics, but its foundation. It governs the structure of atoms, the behavior of electrons in solids, the propagation of photons through space, and the operation of emerging quantum technologies. Superposition gives rise to the complexity and richness of the quantum world, allowing multiple possibilities to coexist until measurement selects one. This coexistence is not a trick or a metaphor. It is the deepest expression of how quantum systems behave. Understanding superposition requires letting go of certain classical assumptions. In everyday life, objects have definite properties long before we observe them. But in quantum mechanics, properties such as position, spin, or energy are not fixed until measured. Until that moment, they exist in superpositions of possibilities, encoded within the wave function. This difference challenges intuition, yet experiment after experiment confirms that nature follows the rules of superposition with unwavering consistency. The idea that a particle can be in many states at once, that atoms can be in two locations simultaneously, that currents can flow in both directions in a superconductor, and that the polarization of light can exist in overlapping configurations. All these conclusions emerge directly from the mathematics of quantum mechanics. They are not artifacts of theory, but reflections of physical reality. And although decoherence suppresses these behaviors in everyday conditions, the underlying quantum laws remain active even in the objects we perceive as classical. Reflecting on this, one can sense a quiet depth in the way nature works. The surface of the world appears solid and definite, yet beneath that surface lies a landscape of possibilities overlapping and evolving. Every atom in your body once existed in superpositions that determined where it settled, how it bound, and how it interacted with its environment. Every photon that reaches your eyes carries traces of superposition that shaped its journey. Even the most stable objects arise from a foundation of quantum behaviors that allow for multiplicity before collapse. There is a gentle comfort in this idea. The world is not rigid, but flexible at its deepest levels. Possibilities coexist, interact, and resolve into the experiences we observe. As you allow these thoughts to settle, you may find a sense of openness mirrored in the physics itself. The universe is built not from fixed certainties, but from overlapping patterns, quietly evolving until the moment of observation. And just as quantum systems hold many paths before choosing one, so too does each day present a landscape of possibilities that only take shape when you move through them. Chapter 5. Entanglement. Entanglement is one of the most profound and counterintuitive features of quantum mechanics, revealing that the smallest constituents of nature do not behave as isolated objects, but as components of an interconnected whole. In classical physics, two systems have distinct, independent properties unless they physically interact. Quantum mechanics overturns that assumption. When two particles become entangled, they share one quantum state, meaning that their properties cannot be described separately. The system as a whole possesses a single mathematical description, even when the particles are separated by large distances. This shared state persists until an interaction or measurement forces it to change, and the consequences of this unity are often startling to anyone accustomed to classical intuition. The most striking aspect of entanglement appears during measurement. When an entangled particle is measured, the result instantly determines the state of its partner, no matter how far apart the particles have traveled. If the entangled state dictates that their properties must be correlated in a particular way, The moment one particle's property is revealed, the other reflects the corresponding value. This happens even when the particles are separated by kilometers or more. It is natural to wonder whether such a connection implies information traveling faster than light, but quantum mechanics prevents this. The outcome of each measurement is fundamentally random. The correlations appear only when comparing results after the fact. Because no controlled message can be transmitted through this randomness, entanglement does not transmit information faster than light and remains fully consistent with the principles of relativity. Einstein, Podolsky, and Rosen famously challenged the completeness of quantum mechanics, suggesting that entanglement implied the existence of hidden variables, unknown pieces of information carried by each particle that predetermined the measurement outcomes. Their idea preserved classical intuitions about locality and independence. However, later theoretical work revealed that no local hidden variable theory can reproduce all of the predictions of quantum mechanics. This realization led to the development of Bell's inequalities. When physicists performed Bell tests in laboratories around the world, they consistently observed violations of these inequalities. These results proved that local hidden variables could not explain quantum correlations. The entangled behavior of particles is real and irreducible. Quantum mechanics predicts correlations that exceed anything possible in classical models, and experiments confirm this repeatedly, closing loopholes with increasing precision. The remarkable endurance of entanglement becomes evident when entangled particles are separated. Early experiments demonstrated entanglement across small distances, but advances in technology soon pushed the boundaries much farther. Entanglement survives long-distance separation even when particles travel through optical fibers, through the atmosphere, or between ground stations and satellites. Photons remain correlated across kilometers without losing the quantum signatures that define their relationship. In some cases, entanglement has been demonstrated over distances approaching the scale of entire cities or between Earth and orbiting satellites. These experiments underscore that entanglement is not a fragile mathematical construct, but a robust physical phenomenon capable of surviving travel through imperfect channels. This robustness supports the development of emerging quantum technologies. One of the most celebrated applications is quantum teleportation, which uses entanglement to transfer the state of one quantum system to another without physically moving the original particle. Teleportation does not send matter itself, nor does it transmit information faster than light. Instead, the process relies on preparing two particles in an entangled state, and then performing a carefully chosen joint measurement on one of them, along with the particle whose state is to be transferred. The outcome of this measurement, combined with classical communication of its result, allows the distant particle to adopt the exact quantum state of the original. Teleportation illustrates how entanglement can be used to move quantum information in ways that have no classical analog. Entanglement also influences how physicists understand the structure of complex quantum systems. Entanglement entropy, a measure of how strongly different parts of a system share information, reveals patterns that classical probability cannot describe. When researchers quantify entanglement entropy in many body systems, they uncover links between quantum information and space-time geometry. In some theoretical frameworks, the fabric of space-time itself appears to emerge from the structure of entanglement in an underlying quantum system. The smoothness of space-time, the behavior of black hole horizons, and even the connectivity of different regions of space may depend on how quantum states intertwine. While these ideas remain under active investigation, they suggest that entanglement may play a foundational role not just in quantum particles, but in the architecture of the cosmos. As these ideas develop, entanglement is becoming a practical resource for building quantum networks. A future quantum internet would rely on entangled nodes that share quantum states across long distances. Distributed entanglement allows quantum information to move securely, enables coordinated operations between remote quantum processors, and provides new ways to synchronize clocks or detect subtle environmental changes. Because entanglement correlations cannot be copied through classical means, they protect communication channels from eavesdropping. Any attempt to interfere with an entangled connection disrupts the correlations and becomes immediately detectable. These properties make entanglement essential for next-generation cryptography and communication protocols. Some theories extend the significance of entanglement even further, proposing connections between quantum correlations and gravity. In particular, certain approaches to quantum gravity suggest that space-time curvature might arise from the pattern of entanglement between quantum degrees of freedom. The geometry of space, in this perspective, is not a passive stage on which physics unfolds, but a consequence of deep informational relationships. Black hole thermodynamics, holographic principles, and emergent gravity theories all point toward a possible unity between geometry and entanglement. If these ideas continue to gain support, they may reshape our understanding of both gravity and quantum mechanics, revealing that the universe's structure depends not just on matter and energy, but on the intricate stitching of entangled states. To understand entanglement more intuitively, imagine that two particles do not each carry separate sets of properties. Instead, the only complete description is the joint state that encompasses both. When the particles are separated, this joint description does not break apart. It remains intact, spanning distance without weakening. When a measurement occurs, it does not send a signal from one particle to the other. Rather, the measurement reveals information about the joint state. The correlations appear instantaneous because they were already embedded in the system. The particles behave as two aspects of one entity, not as independent objects. This unity persists until further interactions disturb the entanglement, and decoherence reshapes the structure of their shared state. Decoherence plays an important role in limiting where entanglement can be observed. Interactions with the environment cause entangled states to degrade as information leaks out into surrounding systems. Macroscopic objects experience decoherence rapidly, making entanglement difficult to observe at everyday scales. Yet even in the macroscopic world, entanglement is present within quantum fields and collective excitations. It is simply hidden by the overwhelming influence of environmental interactions. In carefully controlled laboratories, researchers can isolate systems enough to preserve entanglement for meaningful periods, enabling quantum experiments and technologies that operate at scales once considered unreachable. Entanglement is not merely an exotic feature of quantum mechanics. It is woven into the foundation of physical reality. It determines how quantum systems store information, how they evolve, and how they interact. It provides the fuel for quantum computers, the security of quantum communication, and the theoretical underpinnings of ideas linking quantum physics to space-time. The discovery that nature allows such strong correlations, independent of distance, reshaped our understanding of what it means for physical systems to be connected. As you reflect on entanglement, you may find a quiet sense of wonder in how deeply it challenges ordinary notions of separateness. Particles that once interacted remain linked across vast distances, carrying echoes of their shared past. The world you inhabit is built from atoms and fields that contain networks of quantum correlations stretching back through time. Even your own body, composed of particles drawn from ancient stars, reflects the deep relational structure of the universe. And in this recognition, there is a gentle existential comfort. You are part of a cosmos in which nothing is ever entirely alone. Beneath the surface of everyday experience lies a tapestry of connection that binds distant objects, distant events, and distant moments into a coherent whole. As you let the day settle, you might take ease in knowing that at the deepest level, the universe is held together not by isolation, but by relationship. Chapter 6. Quantum Forces. In the quantum view of nature, forces are not invisible pushes or pulls acting across space, but interactions arising from the behavior of underlying quantum fields. Every force we observe in the universe emerges from these fields and the particles that mediate them. This framework, known as quantum field theory, replaces the classical picture of forces with one where particles interact by exchanging discrete packets of energy carried by force-mediating particles. These interactions explain the structure of atoms, the existence of matter, the fusion processes powering stars, and even the faintest whisper of particles passing unnoticed through the Earth. Understanding quantum forces means understanding how the universe holds itself together at the smallest scales. The electromagnetic force provides one of the clearest examples. Photons mediate electromagnetic forces, linking charged particles through the exchange of these massless quanta. When two electrons repel each other, the interaction can be understood as a continuous exchange of virtual photons, tiny disturbances in the electromagnetic field that carry momentum between the particles. Because photons have no rest mass, the electromagnetic force extends over long distances without fading rapidly. This long reach underlies the structure of atoms, the formation of molecules, and the behavior of light. Electromagnetism is not simply a classical field, but a quantum one, with photons acting as its messengers. Without these photon-mediated interactions, atoms would not bind, and chemical structures would not exist. The strong force reveals a different and more dramatic character. Gluons bind quarks inside nucleons, protons and neutrons, ensuring that the fundamental constituents of matter remain confined. Quarks carry a property known as color charge, and gluons respond to this charge in a way that differs fundamentally from electromagnetic interactions. While most forces weaken with distance, the strong force grows with distance, meaning that attempting to pull quarks apart only increases the strength of the force between them. At some point, the energy invested in separating quarks becomes large enough to produce new quark-antiquark pairs, preventing any isolated quark from appearing. This phenomenon, called confinement, explains why quarks are always found in groups and never alone. The strong force acts over extremely short distances, but within that realm it is the dominant force, shaping the structure of atomic nuclei and playing a central role in the stability of matter. The weak force operates in a subtler way. It governs radioactive decay, allowing certain particles to transform into others. The weak force enables radioactive decay by changing the types or flavors of quarks within particles, causing neutrons to turn into protons or vice versa. This interaction is responsible for the beta decay observed in many isotopes and plays a crucial role in the nuclear processes inside stars. The weak interaction is carried by W and Z bosons, massive particles whose large mass limits the range of the weak force to extremely short distances. The heaviness of these bosons makes the weak force feeble compared to electromagnetism or the strong interaction, yet its existence is essential to the balance of processes that drive stellar nucleosynthesis and radioactive transformations. The Higgs field adds another layer of structure to the quantum landscape. Interactions with the Higgs field give particles mass, embedding a mechanism that distinguishes massless particles, such as photons, from massive ones such as W and Z bosons or electrons. Particles moving through the Higgs field experience resistance, much like objects moving through a medium, and this resistance is what appears macroscopically as mass. Without the Higgs field, fundamental particles would move at the speed of light and would be unable to form stable atoms or structures. The discovery of the Higgs boson confirmed this mechanism experimentally and completed the Standard Model's picture of how forces and particles are connected. While electromagnetism, the strong interaction, and the weak interaction all have established descriptions within quantum field theory, gravity remains more elusive. Classical gravity, described by general relativity, models gravity as the curvature of space-time caused by mass and energy. But many theoretical efforts explore the idea that gravity might arise from quantum states, perhaps emerging from entanglement patterns or from collective behaviors of underlying quantum degrees of freedom. Some approaches suggest that space-time geometry itself could be a manifestation of quantum information encoded in entangled fields. Although a complete quantum theory of gravity remains under development, the idea that gravity emerges from quantum interactions reflects the wider trend of viewing all fundamental forces as rooted in quantum behavior. Quantum forces also play essential roles in processes that power the universe. Nuclear fusion requires quantum tunneling, allowing atomic nuclei to overcome the repulsive electromagnetic barrier between them. In classical physics, two positively charged nuclei could not fuse at the temperatures found in most stars because their thermal energy is insufficient to push them close enough for the strong force to bind them. Yet fusion happens because quantum tunneling allows the nuclei to slip through the barrier with a small but significant probability. This quantum effect fuels stars, creating the energy that lights galaxies and provides the conditions for life. Tunneling illustrates that quantum forces do not merely supplement classical behavior. They replace classical expectations with probabilistic outcomes that shape the evolution of the cosmos. Neutrinos, some of the most enigmatic particles in nature, offer further insight into quantum forces. These nearly massless particles interact only via the weak force, allowing them to pass through matter nearly unhindered. Yet, they possess another striking property. Neutrinos oscillate between flavors as they travel. A neutrino produced as one flavor can later be detected as another. This oscillation arises from the quantum mixing of neutrino states and the fact that neutrinos have small but non-zero masses. Neutrino oscillations reveal that the weak interaction is deeply tied to quantum coherence and probabilistic state evolution, even over cosmic distances. Each neutrino streaming from the Sun to Earth carries within it the signatures of quantum transitions that unfold silently across space. Together, these interactions demonstrate that all forces emerge from quantum fields. Each field permeates space, and particles interact by exchanging excitations of these fields. The idea of a force becomes inseparable from the idea of a field. This framework unifies seemingly different phenomena under a single conceptual roof. Electromagnetism becomes the interplay of electric and magnetic field excitations carried by photons. The strong force emerges from the gluon field, and the color charges carried by quarks. The weak force becomes the exchange of W and Z bosons through the weak field. Even gravity, in some theoretical explorations, may arise from deeper quantum correlations rather than an independent classical curvature of space-time. Understanding quantum forces illuminates the hidden dynamics underlying familiar phenomena. Every spark of electricity, every nuclear reaction inside a star, every decay of a radioactive isotope, and every binding interaction within the nucleus depends on quantum forces operating at scales beyond direct perception. The universe is not held together by rigid classical laws, but by a network of quantum relationships that define how fields interact and how particles exchange information. Reflecting on these ideas reveals a world far subtler than surface experience suggests. Forces that seem invisible and continuous in daily life are, at their core, exchanges of quanta and shifts in quantum fields. The stability of your own body depends on photons mediating electromagnetic interactions, gluons binding quarks, and weak interactions guiding processes that helped form the elements long before Earth existed. Even gravity, the force that anchors you to the ground, may be woven from quantum ties that extend deeper than space-time itself. There is a quiet existential comfort in recognizing this underlying structure. The universe is not chaotic or disconnected. It is held together by patterns that stretch across scales, from the smallest quarks to the largest stars. Every force that shapes your world is an expression of these quantum fields interacting in their patient, enduring way. As you let the day dissolve into quiet, you can trust that the same quantum forces that guide galaxies also guide the particles within you, connecting you to a wider cosmos in ways both intricate and profound. Chapter 7: Quantum Materials. Quantum mechanics does not only govern isolated particles and microscopic interactions, it shapes the behavior of entire materials, giving rise to phases of matter that cannot be explained using classical physics. These materials display properties that emerge from quantum interactions among many particles acting together, often revealing collective behaviors that seem to defy intuition. While everyday matter appears stable and predictable, certain materials reveal the full richness of quantum mechanics on macroscopic scales, offering insights into fundamental physics and enabling technologies that range from quantum computing to advanced sensors. One of the most striking examples of a quantum material is the superconductor. Superconductors conduct electricity with zero resistance, allowing electric currents to flow indefinitely without energy loss. This phenomenon does not merely improve conductivity, it eliminates electrical resistance entirely. In classical materials, electrons scatter off impurities, lattice vibrations, and other electrons, producing resistance and heat. In a superconductor cooled below its critical temperature, electrons no longer behave as independent particles. Instead, they form Cooper pairs, quantum-bound electron states that move through the lattice in a coordinated, wave-like fashion. These pairs condense into a single coherent quantum state that spans the entire material. Because Cooper pairs act collectively, the scattering that normally causes resistance becomes impossible. The current flows without degradation, and magnetic fields are expelled through a phenomenon known as the Meissner effect, further demonstrating the quantum nature of superconductivity. Another profound quantum material is the superfluid. Superfluids flow without friction, exhibiting motion that seems to ignore classical constraints. Helium, when cooled near absolute zero, transitions into a superfluid state where it crawls up container walls, passes through microscopic channels with no resistance, and circulates endlessly in closed loops without losing energy. This behavior arises because the atoms in a superfluid occupy the same quantum state, forming a macroscopic wave function that describes the fluid as a unified system rather than as individual atoms. The lack of friction is not a property of the atoms themselves, but of the collective quantum state they form. Superfluidity illustrates how quantum coherence can produce behavior that defies classical intuition, creating a fluid that behaves more like a wave than a conventional liquid. Closely related to superfluidity is the concept of the Bose-Einstein condensate, a state of matter predicted in the early 20th century and first created experimentally decades later. Bose-Einstein condensates act as single quantum objects, with many atoms collapsing into the lowest available energy state. When this happens, distinctions between individual particles fade, and the entire condensate is described by one wave function. Experimental observation of such condensates reveals behaviors like interference between condensate clouds and coherent spreading consistent with quantum wave evolution. These condensates allow researchers to study quantum mechanics at scales large enough to observe directly, offering a unique window into the boundary between microscopic and macroscopic physics. Quantum effects also manifest in materials with unusual electronic properties, such as topological insulators. These materials conduct electricity only on their surfaces, while acting as insulators in their interiors. The conductive surface states arise from the material's topological properties, which are mathematical features describing how the electronic wave functions behave under certain symmetries. Topological insulators are robust against impurities and structural imperfections, allowing electrons to move along the surface with minimal scattering. Their existence demonstrates that quantum materials cannot be fully understood in terms of local interactions alone. Global properties of the wave function determine their behavior. Another example is graphene, a single layer of carbon atoms arranged in a hexagonal lattice. Graphene electrons behave like massless particles, moving at high velocities and following linear energy relations similar to photons. This unusual behavior results from the structure of graphene's electronic bands, which create points where the conduction and valence bands touch in a way that mimics relativistic physics. Because of these properties, graphene exhibits remarkable strength, flexibility, and conductivity, and it has sparked interest across physics, engineering, and materials science. The quantum Hall effect further illustrates the depth of quantum behavior in materials. When a two-dimensional electronic system is subjected to a strong magnetic field at low temperatures, the electrical conductivity becomes quantized in discrete values. This quantization is not a small detail. It is exact to astonishing precision. The quantum Hall effects reveal new states of matter that cannot be explained through classical theories. In certain versions, known as fractional quantum Hall states, electrons behave as if they split into quasi-particles carrying fractions of the electron's charge. These exotic states arise from collective interactions among electrons, forming quantum fluids with intricate internal structure. Magnetic materials also reveal quantum complexity through the behavior of spin liquids. In ordinary magnetic materials, spins tend to align in regular patterns, either parallel or antiparallel. But in a spin liquid, quantum fluctuations prevent spins from settling into any ordered arrangement, even at temperatures near absolute zero. The spins remain in constant motion, maintaining fluctuating configurations that never freeze into a rigid pattern. These materials challenge classical expectations and may hold insights into how entanglement and quantum fluctuations influence the behavior of macroscopic systems. Quantum dots, tiny semiconductor structures containing small numbers of electrons, provide another pathway into quantum material behavior. These dots confine electrons in small regions, creating discrete energy levels similar to those in atoms. Because of their quantized structure, quantum dots emit tunable photon colors when electrons transition between energy levels. By controlling the size and composition of a quantum dot, scientists can precisely tune the color of light it emits. This property is used in advanced display technologies, biomedical imaging, and quantum communication. Quantum dots highlight how materials engineered at nanoscales can take on properties normally associated with atoms and molecules. Perhaps most remarkably, some materials exhibit macroscopic quantum coherence, meaning that quantum phases and wave functions extend across regions large enough to see with the naked eye. Superconductors, superfluids, Bose-Einstein condensates, and certain magnetic materials all fall into this category. In these systems, coherence is not confined to a single particle, but becomes a feature of the entire material. This coherence allows for persistent currents, interference patterns, and other effects typically associated with isolated quantum systems. Observing such phenomena at macroscopic scales challenges the assumption that quantum mechanics applies only to microscopic entities. In reality, quantum mechanics governs all scales. It simply becomes harder to maintain coherence as systems grow and interact more strongly with their environments. Quantum materials demonstrate that the classical picture of matter as composed of independent particles interacting through simple forces is incomplete. Instead, quantum mechanics reveals that collective behavior plays a crucial role. Electrons form paired states, atoms collapse into unified condensates, spins fluctuate endlessly without settling, and electronic surfaces conduct without resistance. The behavior of these materials depends on the wave-like nature of particles, the delicate interplay of quantum phases, and the ways in which interactions shape collective states. Each quantum material illustrates a specific way in which nature transcends classical expectations. Superconductors show how electrons can cooperate rather than scatter. Superfluids show how liquids can flow without viscosity. Bose-Einstein condensates show how matter can behave as a single wave. Topological insulators show how mathematical topology influences physical behavior. Graphene shows how electrons can mimic relativistic particles. The quantum Hall effects show how collective states can give rise to precision quantization. Spin liquids show how fluctuations persist beyond classical order. And quantum dots show how confinement shapes light itself. Reflecting on these materials, it becomes clear that quantum mechanics is not limited to the abstract world of subatomic particles. It shapes entire landscapes of behavior, revealing new phases of matter with properties no classical theory could predict. The quantum world does not stay hidden at small scales. It appears in the laboratory, in engineered structures, and in materials that display coherence, order, and fluidity that challenge our understanding. There is something quietly humbling in recognizing that even the solidity of matter arises from delicate quantum patterns. The materials that build our world, metals, insulators, semiconductors, are all shaped by quantum rules, whether or not we see their subtler features. And beyond these lie materials that reveal quantum behavior directly, showing us that the universe is richer, stranger, and more interconnected than surface experience implies. As you let the ideas settle, you might feel the same calm that comes from contemplating any intricate pattern of nature. Quantum materials show that the smallest patterns, when repeated and allowed to interact, give rise to new forms and new behaviors. Everything you touch is part of this quiet landscape of order and fluctuation, a balance of coherence and complexity. In that sense, you are surrounded by quantum structure every moment, carried within a universe where even matter itself whispers the presence of deeper laws. Chapter 8: Quantum Measurements. Measurement in quantum mechanics is not a passive act. It is an interaction that reshapes the very system being observed. Unlike classical physics, where measuring a property simply reveals a value that already existed, quantum mechanics teaches that measurement collapses the wave function. Before observation, a quantum system exists in a superposition of possible outcomes described by a probability distribution. The act of measurement reduces these possibilities to a single definite result. This collapse is not merely a matter of updating knowledge. It is a change in the physical state of the system, brought about through the interaction between the measuring device and the quantum object. The relationship between measurement and uncertainty is equally fundamental. Quantum mechanics places intrinsic limits on how precisely certain pairs of properties can be known at the same time. The most famous of these restrictions is the uncertainty principle, which states that the more precisely one property, such as position, is measured, the less precisely a complementary property, such as momentum, can be known. This limitation is not due to flaws in measuring devices, but arises from the structure of the wave function itself. Because the wave function encodes probabilities rather than definite values, narrowing it in one domain inevitably broadens it in another. The uncertainty principle places a hard boundary on classical expectations and has been confirmed experimentally through studies of light, matter waves, and atomic behavior. Not all measurements in quantum mechanics must be abrupt or fully destructive. Weak measurements extract partial information from a system without forcing it into a single sharp outcome. In a weak measurement, the coupling between the system and the measuring device is deliberately reduced so that each measurement contributes only a small amount of information. Repeated weak measurements allow researchers to build statistical insight into a property without fully collapsing the wave function. These methods reveal subtle quantum features such as average trajectories of particles in interferometers or small shifts in quantum states that would otherwise be hidden by strong measurement. Weak measurement does not bypass quantum rules, but shows how information can be gradually extracted while leaving some coherence intact. Quantum mechanics contains other surprising effects associated with measurement. The quantum Zeno effect demonstrates that continuous observation can freeze the evolution of a quantum system. If a quantum state is measured repeatedly in rapid succession, the wave function collapses over and over again into the same state, preventing the system from evolving into a different configuration. This counterintuitive behavior arises because evolution requires the wave function to spread or rotate freely. Constant measurement interrupts this process, resetting the system before it has time to change. Experiments with ultra-cold atoms, trapped ions, and superconducting circuits have demonstrated the quantum Zeno effect, confirming that the presence of a measuring device can control the rate of change in a quantum system. When scientists wish to reconstruct an unknown quantum state, they use a technique known as quantum tomography. Quantum tomography reconstructs unknown states by performing many measurements on identically prepared systems, each measurement probing a different aspect of the wave function. Because a single measurement reveals only one outcome, tomography requires a broad set of measurements whose results can be combined mathematically to recover the full quantum state. It is used to verify the performance of qubits, to characterize entangled states in quantum communication experiments, and to study the coherence properties of quantum optical fields. Although tomography does not reveal the wave function of a single system, it allows researchers to piece together the statistical structure of the underlying state with remarkable accuracy. Detectors themselves play an active role in quantum experiments. They do not simply record events, they influence outcomes through interaction. A photon detector must absorb or scatter a photon in order to register its presence. An electron detector must disturb the electron to reveal its location. Even the most refined instruments cannot avoid exchanging energy or momentum with the system. This interaction is precisely what produces the outcome that collapses the wave function. In this way, detectors are not passive observers, but participants in the evolution of the system. Understanding how detectors influence measurements is central to interpreting experiments, especially those involving interference and superposition. Quantum measurements must also contend with noise. Noise arises from quantum fluctuations, tiny, unpredictable variations in fields and particles that occur even in the absence of disturbances from the environment. These fluctuations are a consequence of zero-point motion and the probabilistic nature of the wave function. They cannot be removed in principle, although they can sometimes be minimized or accounted for. In sensitive experiments, such as those involving gravitational wave detection or quantum sensors, quantum noise sets the ultimate limit on precision. Engineers and physicists develop techniques such as squeezing light, entangling states, or altering measurement bases to reduce certain types of noise while accepting trade-offs in others. Noise is not a technological failure. It is a built-in property of quantum fields. Interference patterns provide some of the earliest and clearest demonstrations of quantum measurements. When particles travel through an interferometer without revealing which path they take, interference appears. But interference disappears when which path information exists. Even if no one looks at the path, the mere possibility of determining the path destroys the interference pattern. This sensitivity shows that information itself plays a role in quantum mechanics. It is not the human act of observation that matters, but whether the environment retains distinguishable traces of the particle's path. When such information exists, the wave function collapses into a mixture rather than a coherent superposition, removing the interference. Related to this is decoherence, a process by which quantum states lose their coherence and begin to behave classically. Decoherence turns quantum states classical by entangling them with the environment. Every uncontrolled interaction, scattering with air molecules, absorption of stray photons, thermal vibrations, spreads information about the system into its surroundings. Once coherence is lost, the system can no longer display interference, superposition, or entanglement in any observable way. Decoherence explains why the classical world appears stable and definite even though its constituents obey quantum rules. It also sets practical limits on quantum technologies, which must isolate systems from environmental interactions to preserve coherence. In cutting-edge quantum experiments, precision measurement relies on entangled states. Entanglement enables correlations stronger than classical physics allows, improving measurement sensitivity beyond what is possible with independent particles. For example, entangled photons can be used to enhance phase measurements in interferometers, and entangled atoms can improve the precision of atomic clocks. These techniques exploit quantum correlations to reduce noise or amplify subtle signals. Entanglement-based measurement is becoming essential in fields that demand the highest precision, revealing how quantum information can be harnessed to improve our understanding of physical systems. Together, these principles show that quantum measurement is far more than a simple act of reading out information. It is a dynamic process shaped by interactions between systems, detectors, and the environment. Measurement defines the boundary between possibility and outcome, between the evolving wave function and the single result that enters experience. Through measurement, the quantum world becomes accessible, but only at the cost of altering the very system under study. Reflecting on these ideas reveals how deeply intertwined we are with the systems we observe. Measurement does not merely uncover what exists, it participates in shaping reality at the smallest scales. The certainty we experience in everyday life arises from countless collapses of wave functions, countless acts of decoherence, and countless interactions that stabilize the classical world. And yet, beneath these layers of definiteness lies a realm of possibility, coherence, and fluctuation. There is a quiet comfort in knowing that the universe allows such flexibility at its foundation. Quantum systems evolve through probabilities until an interaction fixes a result. In a sense, the world around you is the product of many such resolved possibilities, each one crystallizing from a cloud of potential. As you rest, you can let these thoughts drift gently through your mind. Just as quantum states transform through interactions, your own experiences unfold through choices, observations, and moments of clarity. And beneath everything, the universe continues its subtle dance of coherence and collapse, patiently shaping reality one measurement at a time. Chapter 9: Quantum Universe. The universe at its largest scales may seem quiet, stable, and governed by smooth, predictable laws, but its history and structure are rooted in quantum mechanics. Long before galaxies formed or stars ignited, the cosmos existed in a state where quantum rules dominated every process. In that early era, tiny fluctuations in quantum fields shaped the future of everything that would ever exist. Quantum fluctuations seeded cosmic structure, imprinting slight differences in density across the young universe. These minute variations, vastly smaller than any particle or atom, were later stretched by cosmic expansion and ultimately became the seeds of galaxies, clusters, and the vast cosmic web visible through modern telescopes. What began as subtle quantum randomness became the scaffolding on which the large-scale structure of the universe would grow. This amplification of microscopic origins was made possible by cosmic inflation, a brief but dramatic period of expansion that occurred in the earliest fraction of a second of cosmic history. Inflation magnified microscopic variations to macroscopic scales, stretching the quantum fluctuations into large regions of space. The smoothness of the universe on the largest scales, combined with the small variations detected in the cosmic microwave background radiation, supports the idea that inflation operated on quantum origin structures. Inflation did not erase the quantum imprints in space, it enlarged them. These imprints became the initial density variations that gravity later amplified into galaxies, stars, and planets. The universe as we know it is therefore inseparable from the quantum fluctuations that shaped its first moments. Quantum mechanics also influences some of the most extreme environments in the cosmos. Near black holes, where gravity becomes extraordinarily strong, quantum effects play a crucial role. Hawking radiation is a quantum effect near black holes, arising from interactions between quantum fields and curved spacetime. In the vacuum near the event horizon, virtual particles continually appear and vanish as part of the natural fluctuations in quantum fields. Under the extreme gravitational conditions near a black hole, one member of a virtual particle pair may escape to infinity while the other falls into the hole. The escaping particle becomes real, producing a faint glow of radiation that slowly carries energy away. This process implies that black holes are not completely black, but lose mass slowly over immense time spans. Hawking radiation connects gravity, quantum mechanics, and thermodynamics in a way that hints at deeper unifying principles. Quantum theory also reveals that even empty space is far from empty. Virtual particles fill the fabric of space, appearing briefly as fluctuations in quantum fields before annihilating. These transient excitations contribute to the energy of the vacuum and influence large-scale cosmic behavior. Vacuum energy affects cosmic expansion by acting as a form of pressure or tension within spacetime. In modern cosmology, vacuum energy is associated with dark energy, the phenomenon driving the accelerated expansion of the universe. Although scientists continue to investigate the exact nature of dark energy, the idea that quantum vacuum energy plays a role remains a central possibility. The quantum vacuum is not a passive background, but an active component of cosmic evolution. As physicists explore deeper connections between quantum mechanics and cosmology, one major goal is the development of a theory of quantum gravity. Quantum gravity aims to unify all forces by providing a consistent description of gravity within the quantum framework. Traditional quantum field theory describes electromagnetism, the weak interaction, and the strong interaction successfully, but gravity stands apart in classical theory. At extremely small scales, classical descriptions of gravity break down, and a quantum theory becomes necessary. Many research programs, including approaches involving strings, loops, or holographic principles, attempt to map out this unification. While a complete theory remains elusive, these efforts often point toward a surprising conclusion. that space and time may not be fundamental ingredients, but may arise from deeper quantum relationships. One compelling idea is that space-time may be built from entanglement. In certain theoretical contexts, the geometry of space-time appears to emerge from the pattern of entanglement among underlying quantum degrees of freedom. According to these models, the smoothness of space-time and the connectivity of distant regions reflect the strength and structure of entanglement in a deeper quantum system. If regions of space-time are highly entangled, they appear close together. If entanglement is reduced, they appear farther apart. This perspective suggests that space-time geometry is not a static fabric, but a dynamic manifestation of quantum information. Although these ideas remain theoretical, they hint at a future where geometry, gravity, and quantum mechanics are understood as different expressions of the same underlying structure. Even the universe itself may behave like a quantum wave function. Some interpretations of quantum cosmology propose that the entire universe can be described by a single wave function that encodes every possible configuration of matter and energy. This wave function evolves according to quantum rules, determining the probabilities of different cosmic histories. In this framework, classical spacetime emerges only when certain quantum variables take on definite values through processes similar to decoherence. Although this approach remains conceptual, it highlights the possibility that the universe is fundamentally quantum, and classical reality arises only as a kind of large-scale approximation. Black holes also provide insight into how quantum information may be stored in the universe. According to holographic ideas, black holes may store information holographically, meaning that the information about objects falling into a black hole is encoded on its surface rather than lost inside. This idea is linked to the concept that the amount of information in a region of space is proportional to the area of its boundary, not the volume. The holographic principle has profound implications for cosmology because it suggests that the universe itself may obey similar informational limits. In such a universe, what we perceive as three-dimensional space might be described fully by information encoded on a distant boundary. This principle connects quantum information, thermodynamics, and space-time in a unified mathematical structure. The physics of the early universe was entirely quantum. Temperatures, densities, and energies were so high that classical concepts lose meaning. During its earliest moments, particles did not behave as isolated entities but existed as excitations of unified quantum fields. Interactions between these fields shape the cosmic evolution, generating matter, radiation, and the seeds of structure. Even the formation of fundamental particles depended on quantum processes, including symmetry breaking, tunneling events, and transitions in the fields shaping the dynamics of space-time. To understand the first seconds of cosmic history, scientists must draw on both particle physics and quantum field theory, combining them with models of gravity to reconstruct a picture of the universe's origin. Quantum mechanics therefore permeates the entire cosmic timeline. It shaped the earliest fluctuations, guided inflationary expansion, influences black hole behavior, and contributes to the accelerated growth of space today. Even the questions surrounding dark matter, dark energy, and the ultimate fate of the universe may require quantum explanations. The ongoing search for quantum gravity suggests that space-time itself emerges from quantum behavior, and holographic ideas imply that information plays a central role in structuring the cosmos. Reflecting on these ideas reveals a universe far stranger and more interconnected than everyday experience implies. The galaxies scattered across billions of light years, the stars burning with nuclear light, the quiet beam of a photon traveling through darkness, all owe their existence to quantum rules acting at unimaginable scales. The atoms in your body and the clusters of galaxies at the edge of the observable universe are shaped by the same underlying quantum laws. There is a quiet comfort in knowing that the cosmos, vast as it is, grows from subtle fluctuations and deep connections. Just as the universe emerged from a cloud of quantum possibilities, every moment of your life unfolds from choices, interactions, and patterns that define your own path. And beneath both, there is a single reality shaped by the delicate rhythms of quantum mechanics, holding everything, stars, space, and you, within its wide, evolving wave. Chapter 10. Quantum Technology. Quantum mechanics, once regarded as a theory relevant only to atoms and subatomic particles, has become the foundation of a growing technological revolution. Many of the devices that define modern life operate because of quantum principles. Others, still in development, promise to reshape computing, communication, sensing, and our understanding of physical systems. Quantum technology does not simply use quantum mechanics to explain nature. It uses quantum rules to engineer systems that surpass the limits of classical physics. These technologies demonstrate how the abstract features of quantum theory, superposition, tunneling, quantization, entanglement, and wave function dynamics, can become tools for practical, measurable advancement. Lasers are among the earliest and most transformative quantum technologies. Lasers rely on quantum energy transitions, using the fact that electrons in atoms and molecules can occupy only discrete energy levels. When an electron is excited to a higher level and then allowed to fall back to a lower one, it releases a photon with a precise wavelength determined by the difference between those energy levels. In a laser, this process is controlled and amplified. A collection of atoms is prepared so that many electrons sit in excited states. When one electron emits a photon, that photon stimulates another excited electron to drop to a lower state and emit an identical photon. This chain reaction generates a beam of coherent light with a narrow spectrum and a precise direction. Lasers are used in communications, medicine, measurement, and countless areas of research. Their accuracy and power arise directly from quantum transitions and the quantized nature of atomic energy levels. Another technology built on quantum transitions is the atomic clock, which counts time based on electron jumps between energy states. Atomic clocks count electron jumps with extraordinary precision because the frequency associated with these transitions is stable, reproducible, and fundamentally tied to quantum structure. Modern atomic clocks measure time so accurately that they would drift by only a small fraction of a second over the age of the universe. This unprecedented stability underpins global positioning systems, telecommunications networks, and scientific experiments that require exact timing. By using quantum transitions rather than mechanical or electronic oscillators, atomic clocks set the standard for how time is defined and measured. Quantum computing extends quantum principles into an entirely new domain. Traditional computers encode information using bits that represent either 0 or 1. Quantum computers use qubits, not bits, and qubits can exist in superpositions of 0 and 1 simultaneously. This property allows quantum computers to explore multiple computational pathways at once. When combined with entanglement and interference, qubits enable algorithms that can solve certain problems far more efficiently than classical computers. Quantum computing is still in development, with challenges involving decoherence, noise, and error correction. Yet progress continues steadily, and quantum processors based on trapped ions, superconducting circuits, and photonic systems already demonstrate tasks beyond the abilities of early classical machines. Quantum computers may one day revolutionize cryptography, optimization, simulation, and the design of new materials. Quantum cryptography takes advantage of the fundamental limits of measurement. In classical communication, signals can be intercepted without necessarily being detected. Quantum encryption detects eavesdropping automatically because measurement collapses quantum states. If a third party attempts to read quantum encrypted information, the act of measurement alters the states being transmitted, revealing the intrusion. This principle ensures that secure keys can be generated and shared in ways that guarantee integrity. Quantum key distribution systems are already operational in some locations, establishing secure communication links that cannot be silently compromised. As quantum technologies expand, such systems may become central to protecting sensitive information. Quantum principles also underpin several widely used diagnostic and imaging tools. MRI machines read nuclear spin behavior, detecting how atomic nuclei respond to magnetic fields. The spins of nuclei precess at specific frequencies determined by quantum rules. When electromagnetic pulses are applied, the spins shift into excited states, and as they relax back, they emit signals that reveal the density and environment of nuclei in the body. MRI does not expose patients to ionizing radiation and provides detailed images of soft tissues. Its effectiveness depends entirely on quantum behavior at the nuclear scale, converted into macroscopic diagnostic information. Modern electronics owe their existence to quantum effects as well. Transistors depend on quantum tunneling, allowing electrons to pass through barriers they could not cross in classical physics. Quantum tunneling becomes essential as transistor components shrink to nanoscales, where classical conduction models fail. Without tunneling, modern semiconductor devices would not function, and the trend toward ever smaller and more powerful electronics would have ended long ago. Although tunneling poses challenges such as leakage currents, engineers have learned to design materials and structures that harness or mitigate these effects. Semiconductors themselves rely on band gaps created by quantization. In a semiconductor, electrons occupy energy bands separated by gaps where no electron states exist. These bands and gaps arise from the quantized nature of electrons in a crystalline lattice. The ability to precisely engineer band structures enables transistors, solar cells, diodes, and LEDs. When electrons transition across band gaps, they absorb or emit quantized amounts of energy. This behavior is central to modern electronics and illustrates how quantum mechanics underlies even the simplest electrical components. LEDs provide a clear example of quantized energy release. LED light emission is quantized photon release, occurring when electrons drop from higher to lower energy states in a semiconductor. The color of the emitted light depends on the size of the band gap. That is why LEDs can be engineered to emit specific wavelengths, enabling displays, lighting, fiber optic communication, and scientific instrumentation. The quantum design of semiconductors allows for precise control over color, efficiency, and brightness. Quantum technology also enhances sensing. Quantum sensors detect tiny gravitational changes, magnetic fields, temperature variations, and accelerations with sensitivities beyond classical limits. By using entangled states or superpositions, quantum sensors overcome noise that restricts traditional devices. They are used in navigation systems, geological surveys, medical diagnostics, and fundamental physics experiments, such as dark matter searches and gravitational wave detection. These sensors rely on the fragile yet precise nature of quantum coherence, using it to measure quantities that would otherwise remain hidden. Finally, quantum simulators model complex physical systems that classical computers cannot handle. Many systems in chemistry, condensed matter physics, and material science require tracking enormous numbers of quantum states. Classical computing becomes infeasible because the number of states grows exponentially with system size. Quantum simulators, created using cold atoms, trapped ions, or superconducting arrays, reproduce the dynamics of these systems directly. They allow scientists to study exotic phases of matter, quantum phase transitions, superconductivity, and properties of molecules with unprecedented accuracy. Quantum simulators open a pathway to understanding phenomena that remain inaccessible through conventional computation. Together, these technologies show how deeply quantum theory shapes our modern world. Lasers beam coherent light across communication networks. Atomic clocks define global time. Transistors and semiconductors power computers. LEDs illuminate homes and screens. MRI machines reveal the structure of the human body. Quantum cryptography protects information. Quantum sensors measure the faintest shifts in nature. Quantum computers and simulators promise to expand the frontiers of knowledge. Each of these advances grows from quantum principles once thought relevant only to abstract theory. Reflecting on this, it becomes clear that quantum mechanics is not a distant concept locked in laboratories. It is woven into the tools, devices, and systems that shape daily experience. When you read a message on a screen, quantum tunneling and semiconductor quantization ensure the electrons move correctly. When you navigate using GPS, atomic clocks based on quantum transitions guide you. When a laser scans or measures, it draws on the purity of quantum energy levels. Behind every technological step forward lies a deeper quantum story. There is something quietly humbling in realizing how much of the modern world rests on rules that defy classical intuition. The devices that light your room, connect you to distant places, or depict the structure of your own body all depend on the behavior of electrons and photons moving through states described by wave functions. The universe does not simply support these technologies, it enables them through its most fundamental laws. And in this recognition, there is a calm reminder of how deeply connected you are to the structure of reality. Whether you think of the quantum states guiding an atomic clock or the photons emerging from an LED, these processes unfold continuously around you. They reveal a universe in which the smallest scales give rise to the largest changes. As you settle into rest, you might reflect on how your own life is intertwined with these subtle quantum processes, each one a quiet bridge between theory and experience, between the invisible and the familiar. My friend, if you're still awake, I'm glad you traveled through this quantum world with me. And if sleep found you along the way, that's exactly what this video was meant to do. But if your eyes are still open, there's another journey waiting for you. Another gentle story about the universe, ready to guide you deeper into rest. Until then, sweet dreams among the stars.